Hello, my name is Shahryar Shahryari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action. This particular lecture is on cosets of a subgroup. The theme in my book is that you learn a lot by focusing on actions of groups. When groups act, that's when you get to know them. This lecture will be an example of such a thing. We will have a subgroup act on the group, and as a result, define cosets. So G is a group and H is a subgroup of G. When we have the less than or equal to sign, that means that H is not just a subset of G, but it's actually a subgroup of G. Now we know that H can act on G by left multiplication. Let me remind you what that means. When we say a group acts on a set, the way we're thinking about it is that we have a group, maybe we are holding it in our hand, and we have a set, maybe it's sitting on the floor, and every group element, you can throw it at the set and it'll permute the elements of the set. Every group element gives you a permutation of the elements of the set. In this case, the group is that subgroup, and the set is actually the group. So G is the set that's sitting on the floor. H, the subgroup, is in my hand, and I'm going to throw the elements of the, in this case, H, onto G, and I will get a permutation on elements of G. And how does that permutation work? It's just left multiplication. So if H is in H, the group element, and I throw it at the set element G, then H dot G, that's the result of applying H to G, is HG. And what's HG? It's the product of H and G. Since after all, both H and G are in the group G, we can actually multiply them. This is an action because to be an action, to get that permutation, you need two properties. You need that the identity doesn't move anything. And of course, E dot G here is just going to be EG, the product of E and G, and that's G. So the identity element of the group H that fixes every element does not move them as it should. If I apply two elements of the group in succession, so K applied to G, K dot G, and then H acts on that, then what do I get? Well, K dot G is KG. So I have H dot KG, and H dot KG is HKG. Now, HKG is actually exactly the same as HK dot G. And to be an action, you have to have these two properties. Identity doesn't move anything. And if you have H act on K dot G, then the result should be the same as HK dot G. In other words, the action should respect group multiplication, and it does. So we do have an action. And whenever we have an action, there are certain general questions that we ask. In particular, to begin with, we ask, what are the stabilizers? What are the orbits? What are the stabilizers of the action? What are the orbits of this action? We'll ask this question about any particular action that you run into. Let's start with stabilizers. You ask, what's the stabilizer of an element of the set? You pick one element and you say, what's your stabilizer? Now that means, what are the elements of the group that fix that element, that when you apply them, it does not move? So we ask, what's the stabilizer in H of X? X is an element of the set, H is the group, and so by definition, that's all the elements in H such that H dot X equals X. The reason we're interested in this, by the way, is that the thing we know about stabilizers is that they're subgroups, and so they could be interesting subgroups of our group. In this case, H dot X is HX. So for which H is HX equals X. But if you have HX equals X, we are in a group, we have right cancellation. We can cancel X's. That amounts to multiplying both sides by X inverse. And you get H's identity. So the only element that fixes X is identity. And so the stabilizer is actually not that interesting. Let's look at orbits. Point of view is that you have an action, you check the stabilizer in orbits and hope for the best. Orbits of what? Again, orbits of the set elements. Again, you pick a set element and ask, what is its orbit? So I picked X in G, and I want to know what's the orbit of that. What's the orbit mean? Orbit is all the other elements in the set that you can get to via the action of the group. So when you take different elements of the group and apply it to that one element, it goes to different places. All those different places, though, that's the orbit of that element. X is in G, so, and we say the orbit in G of X. Now, G here is the set. The stabilizer lives in the group, the orbit lives in the set. What's good about orbits? They partition the set. Two things you should know if you know nothing else about actions is that when a group acts on a set, you get stabilizers and you get orbits. Stabilizers are in the group and they're subgroups of the group. Orbits are in the set, and the set of all orbits partitions the set. What's the orbit of X in G in the set? and it consists of all the elements of the set such that you can get to them from X by the action. There's some H that H dot X will give you that element. And so what are those? Now, H dot S is HX. So what we really want is all the elements of the form HX. To find the orbit of X, we just keep multiplying it by elements of H, and everything we get is going to be in the orbit. Now, this set, the set of elements of the form HX, where when H is in H, we denote it by capital HX. So HX is the set of all the elements of the form little h times X, where H is in H. And so these are the orbits. But because this is such a special orbit of this particular action, and we want to use it all the time, we give it a different name. Important orbits, important stabilizers, get their own name. So H is a subgroup of G, X is an element of G. Those are the ingredients you need to define one of these orbits. Then HX, which is all the elements of the form little h times X, you take elements of the subgroup H and multiply them by that guy X, you call that HX. That's called a right coset of H in G. It's the right coset because you're multiplying X on the right. In the same manner, X times H is called a left coset of H in G. Of course, if the group is abelian, these two things will be the same. If the group is not abelian, they don't have to be the same. Sometimes they are, sometimes they're not, and that actually ends up being an important distinction. Here we already have a corollary. G is any group, and you pick a subgroup, your favorite subgroup, then the right cosets of H in G partition G. And I've already discussed why this is. The reason for that is that the right cosets are orbits of an action, and orbits always partition. Could we have done this slightly differently? So if H is a subgroup of G, and if we try to define the action of H on G by right multiplication, so define H dot X to be XH, then we do not get an action. Identity works fine, but the other property doesn't quite work. So if you look at H dot K dot X, this time is H dot XK, nothing wrong with that, and that's X times KH, and there's nothing wrong with that either. However, that's not the same as X times HK, which is what we would get if we have HK act on X. So the property of actions that we would like would not follow. So, and that's because KH and HK does not have to be the same. However, if we really want to have an action on the right, we can do that. We just have to modify things slightly. So if H does act on G, if you define H dot X to be XH inverse, so you have to throw in an A inverse there. Why would that work? The identity still works. And this time, H dot KX, what is that equal to? Well, K dot X this time is XK inverse. And what's H dot that? Well, it's XK inverse H inverse. So what? Well, K inverse H inverse is another name for HK inverse. And this is actually exactly what would happen if HK acted on X. I would get exactly X HK inverse by my new definition. So this does give me an action. And what are the orbits of this? The orbits of this are all the places that I can go via the action of H on X. And this time the action is XH inverse. And so what are those? Those are actually the same as X times all of H. Now you might say, well, there's an H inverse there. What about that guy? Well, the point is that if you have all your group on one side of the room and then go through one at a time and ask, well, who are you? Well, I'm H. Well, who's your inverse? Blah. Send the inverses to the other side. Eventually, you'll have everybody else on that side. So instead of all inverses of the elements of a group is exactly the group itself. Even though one at a time, XH inverse is not the same as XH, when you look at the whole set of XH inverses, you get the same as XHs. And that what that says is that left cosets are the orbits of this action. And so left cosets also partition the group. Let's look at a quick example. Let's say that G is the symmetric group on 3 letters. So it has 6 elements. These are one-to-one onto functions from 1, 2, 3 to itself, or permutations of 1, 2, 3. Let's take one of its subgroups, a subgroup of order 2, identity and 1, 2, and then we can find its right cosets. The easiest right coset to find is the right coset of E, identity. HE is just H, because when you multiply E by the elements of the subgroup, you just get H. But note that this H has another name too, this coset. It's also H times 1, 2. If you take 1, 2 and multiply it in, you get the same set. So H1, 2 is another name for H. And that's not surprising because E and 1, 2 are in the same orbit. And so their cosets are the same. There are other cosets. So h times 1, 3, for example, will be, you have to multiply 1, 3 on the right. E 1, 3 is 1, 3. 1, 2 times 1, 3 is 1, 3, 2. So that's another coset. And this has another name, H132. We already have taken care of 4 of the elements of the group. Remember, cosets partition the whole group. And so the other 2, the remaining 2 are going to be our last coset, H23, and that has a name also H123. The fact that cosets have aliases will come to haunt us. So if a coset walks in, you might say, well, what's your name? And they will say something like, well, HX. But next day, if you ask the same cosets, what's your name? They might say HY. And X and Y might not be the same. That really matters when you're trying to define a function on cosets. We'll see an example of that at the end of this lecture. It's very important to know that hx equals hy. If these 2 right cosets are the same, that does not mean that x equals y. Every coset could have several different names. But what does it mean if hx equals hy? This will happen a lot, and so we need to have a good handle on what does it mean to say hx equals hy. If you have a group and H is a subgroup, then the following statements are equivalent. This means that if any of the statements that I say is true, then all the other ones are true. If any of them is false, all the other ones are false. So what are those statements? The first one is hx equals hy. So the rest of them are going to give us characterizations for when hx equals hy. The second one is that y is an element of hx. The third one is that y equals little h times x for some little h in h. And the fourth one is that yx inverse is an element of H. And in particular, when is it Hg equals H? Which cosets are actually the subgroup? Exactly if and only if G is in H. If you take H times an element of H, you get H. But if you take H times something else, you will not get H for sure. You can do this directly. It's not that complicated without mentioning actions. But if you think of it as actions, it's just like there's nothing to do. So Hx is the orbit of x in the action of H on G by left multiplication. Hy is the orbit of y on the same action. To say that hx equals hy is the same as saying that the orbit of x is the same as the orbit of y, and that's the same as saying that y is in the orbit of x, which is hx. So that first thing is just knowing that these guys are orbits, and therefore, if the orbits are the same, this guy's in that orbit and that guy's in this orbit. And if y is in hx, that's the same as saying that y equals little h times x for some h in h. That's what capital Hx means. And if you have y equals little hx for some h in h, then you can multiply by x inverse on the right and get yx inverse is in h. When is hg equals h? Well, h is the same as he, so now we can use what we have, and that's the same as saying that g belongs to h. So now we want to focus on the size of these right cosets. If you have a subgroup and you have an element x in G, then the size of every right coset is the same as the size of the subgroup. And this means that the size of all right cosets are the same as each other because they're all now the same as the size of the subgroup. Same thing is true for left cosets. In particular, the left cosets and the right cosets are of the same size. Both proofs are similar. We'll do the first. Now, in the case where the subgroup is finite, this is pretty clear. You multiply h by that element x in G, you will get h1x, h2x, hnx, and there's no repeats in this second set, hx, because of cancellation laws. hix equals hjx would mean that hi equals hj. So this set hx also has n elements, and so both of them have the same number of elements, and we are done. But what if h was infinite? And you might say, well, if h is infinite, then you can't talk about the size of h or the size of hx, and you would be right. But actually, I do mean something. So if h is infinite, then by this absolute value of hx equals absolute value of h, I don't mean size, I mean cardinality. So a more general statement is to say that h and hx have the same cardinality, and that applies to whether or not h is finite or not. If you don't know what cardinality is, then watch my video on cardinality. Two sets have the same cardinality if you have a one-to-one onto map from one to the other. If you have a bijection, a one-to-one onto map from one to the other, you're pairing the elements off. You're saying this guy is paired to that one, this one is paired to that one, this one is paired to that one, and so forth. And so if they're finite, then that means they have the same size. But even if they're not finite, we say that they have the same cardinality or they're in a one-to-one correspondence with each other. So if X is in G, I want to give you a bijection from H to HX. So H is the domain, HX is the codomain. I need to give you a function that takes elements of H and gives you elements of HX. Where do you send little h in H? Well, you just multiply it by X and you get HX, and that will be something in the right coset. But I have to prove to you that it's one-to-one and it's onto. So how do I prove it's one-to-one? I assume that H1 and H2 went to the same place and show that they weren't really different to begin with. They were actually the same element. So assume phi of H1 was equal to phi of H2, but what does that mean? Phi of H1 is H1x, phi of H2 is H2x. So this means H1x equals H2 of x, but now I use cancellation on the right, cancel x's, and I will get H1 equals H2. With all these proofs, you should stop the video, do the proof yourself, and then if you get stuck, then you should look at the video. So H1 equals H2, and so those two guys were not different to begin with, and so the map is one-to-one. This is how we prove one-to-one as always. How do we prove that the map is onto? Well, we have to take something in the codomain and show that something hits it. So let G be an element of the right coset HX, and I need to find you something in H such that phi of that thing that I found is G. But if G is in HX, what does that mean? That means that G is of the form little h times x. Otherwise, it wouldn't be in HX for some h in x. And if that's the case, then I know which h is going to be mapped into G, and that's h. Phi of h is going to be hx, but hx is G. So I found you something that hits G, something that's mapped to G via phi, and so phi is onto. And so I've got a one-to-one onto map, and so I just proved that the cardinality of h is the same as the cardinality of xh. So now that we talked about the size, we can talk about an important concept of index. So if G is a group and H is a subgroup of G, the number of right cosets is called the index of H in G and is denoted by this notation, the absolute value sign G colon H. Always read this as the index of H in G. The index of H in G is the number of right cosets of H in G. Now, if the number of right cosets is infinite, and what could be, then we say that the index is infinite. If the subgroup, for example, is the trivial subgroup identity, then the index is all of G. Why is that? Because if the subgroup is identity, then how many cosets this has? Well, it has a lot. Every single element is going to be a coset by itself, because if you take H and multiply it by X, you just get the set consisting of X. So every right coset will have one element. And if H is G, if H is all of G, then that's just the one coset, and coset's partition. There's no room for anybody else. So there's just one coset. The index of H in G is 1. And we are actually ready to state and prove a Lagrange's theorem, which is a very powerful theorem. And in the next lecture, we'll come back to Lagrange's theorem, see like all the mileage we can all of a sudden get just by knowing Lagrange's theorem. But right now, we are ready to say what it is. So if you have a finite group, and if you have a subgroup, then the number of cosets, right cosets, is just the size of the group divided by the size of the subgroup. In particular, the size of the subgroup divides the order of the group. The number of the cosets can't be 3.5. So when you take the order of G divided by the order of H, you should get an integer. And then so that means that H is a factor of G. So that means if you walk into a group of order 12, you will never find a subgroup of order 5. You possibly could find a subgroup of order 1, 2, 3, 4, and 6, and 12. You're not guaranteed those size subgroups, but those are the only things that you could hope for. And that small restriction makes our life so much easier when we're making arguments in finite group theory. Now, what's the proof of this? You already know the proof. I mean, actually just stop the video and try to argue it. It's very straightforward. The right cosets of H partition G, they're all of the same size. What size? The size of H. So you have your group, you have split it up into parts, and each part has size of H. Well, how many parts do you need? Well, you need the size of G divided by the size of H. That's going to be the number of parts, and that's the number of right cosets that you need, and Lagrange's theorem is proved. So I want to finish this lecture by talking about the left index. Now, the left index, all I mean by that, the number of left cosets. The number of left cosets of H in G is the same as the number of right cosets of H in G. So in particular, left index is the same as index. If G is finite, then this is very clear, because the number of right cosets would be the size of G divided by size of H, the number of left cosets would be the same thing because left cosets are also partition and they have the same size as the right cosets. And so, of course, the number of left cosets and right cosets will be the same. I want to actually prove this more generally. And so saying the number is actually not technically correct. What I should really say is that the set of left cosets has the same cardinality as the set of right cosets. And I want to show you a one-to-one onto map. There's a subtext. And the reason I want to do that is not so much that this result is that important, but because I want to show you a warning about when you define functions on cosets, which I already alluded to earlier, but now it's the time to actually see it. So what I want to do is to find a bijection between left and right cosets. I want to define a map, a function that you plug in a left coset and gives you a right coset. And I'm going to use this one. Phi of xh is hx inverse. xh is a left coset and hx inverse is a right coset. So I'm taking a left coset and giving you a right coset. So I'm giving you a function from the set of left cosets to the set of right cosets. But am I? And this is where the aliases come in. See, left cosets as well as right cosets have aliases. Every left coset might have a number of different names. And we used its name to define the function. And that's a problem. Because what if tomorrow we forgot this name and we're using another name and we ended up somewhere else? It's possible that xh equals yh and x is not y. And because of that, we have to show that the map is well defined. What do I mean by that? Well, we have to show that one element in the domain does not go two different places. That's the definition of function. One thing cannot go to different places. And how could that happen here? Well, the same left coset has different aliases. The same left coset under this alias might end up here, under that other alias might end up there. And that's a no-no. If that happens, we don't have a function. So before we can even talk about a phi, we have to make sure that we have defined a function. So the prudent thing is to not use phi while you're trying to prove well-definedness, because you don't really have a function yet. I'm going to say, assume that I have two aliases for this left coset. So I have xh and I have yh, but they're the same. Xh is the same as yh. And what I want to do is I want to say that my rule is going to send these guys to the same place. Regarding of what alias this left coset uses, I'm going to be sending it to that one place. What I have to do is that to show that if the left coset xh is the same as yh, then hx inverse is also the same as hy inverse. Well, if xh is the same as yh, then y is x times h. Let's look at hy inverse. Hy inverse will be xh inverse because y is xh, and xh inverse, again, by the Sachs and Schuss theorem, is h inverse x inverse. But capital H inverse is just h, because h inverse is in h, and we said that if you have the right coset, capital H times some element of that subgroup, you get that subgroup back. And so we're left with hx inverse, which is what I wanted to prove. So I proved that this map is well defined. So I have now a function, a well-defined function, from left cosets to right cosets, and it's defined by sending xh to hx inverse. And I want to show that it's one-to-one. I assume that phi of xh is equals to phi of yh and show that xh equals yh. If you go back, proof of map is well-defined versus one-to-one are sort of the opposite of each other, and that's sometimes confusing to students. Before, we assume that xh and yh are the same and showed that their image is the same. Here we are assuming that their images are the same, and we want to show that they really weren't different to begin with. Well, what is phi of xh? Well, that's hx inverse. What's phi of yh? That's hy inverse. So these must be the same. These guys are the same if y inverse is an element of capital hx inverse. In other words, it's of the form little hx inverse, where little h is an element of the subgroup H. And then what does that tell us about y? Well, y is y inverse inverse. And so y is hx inverse inverse. Again, by Sachs and Schuss theorem, that's x inverse inverse, which is x, times h inverse. So y is xh inverse. But then yh is going to be xh inverse times h, because xh inverse is y. And then again, h inverse times h is h itself. And so yh equals xh, and I've proved to you that the map is one-to-one. I also have to show you that the map is onto, and that's the end of this lecture. To do that, I have to take a right coset and show that it comes from some left coset under this map. So HW, maybe it's an arbitrary right coset of H and G. At this point, I don't know anything about W, but I know which left coset is going to go to it. If you take W inverse H, which is a left coset, and apply phi to it, you will get HW because you get HW inverse inverse, and that's HW. Phi is 1 to 1 and onto, and we have a bijection. And so we proved that the set of right cosets and the set of left cosets have the same cardinality regardless of whether or not we are in an infinite group or a finite group. And this is the end of this lecture. Till next time.